So good morning, I'm Jan-Pieter, and today I'm presenting two talks. So this one will be at PKC, and then there's a second talk at PQC, but they're more or less about the same. This talk is about decryption failures and their effects on the schemes. So it's a merged paper. I will do the first part of the presentation, and the second part will be, well, at PKC, so watch that if you want to have a second part. So it's a merged paper, so it's a paper by Kian Guo, Thomas Johnson, Alexander Nilsson, merged with our paper with Frey and Ingrid and myself. So 2 years ago I was part of the NIST Commission Sabre, and one of the challenges, so Sabre is one of the submissions to the NIST post-quantum standardization effort, in which we are looking for new encryption schemes that are secure against quantum computers. And so one of the challenges that we had when designing the schemes is, of course, the parameter setting. How do we choose our parameters? On one hand, you want your parameters to be small, because then you have small bandwidth and you have fast calculation. But on the other hand, of course, you need to think about the security of the underlying problem. So you need to select your parameters so that your scheme is actually secure. And this is a typical trade-off in most schemes that you look at. Now, there was one thing that we were also dealing with in these decryption failures. Some of these post-quantum schemes, they have a small probability of decryption failures. And when this decryption failure occurs, the two parties that are communicating with each other, they have a very small probability of ending up with a different message or a different key. So they do all these calculations, and in the end they don't get the same message out. And as these decryption failures, well, they depend on the secret. So if one of these decryption failures occurs, then you have some link between this failure and the secret, and you can derive information about the secret. Or you maybe can. Because at the moment that we were working on this, there was not really a lot of work on this. We didn't really know what to choose. There was some provable results in the quantum setting where it seemed to be like squaring the failure probability, but maybe this is too conservative. So we looked into this to see how bad is decryption failures actually were. So before we go into the details, let's present a basic scheme based on the LWE hard problem. So what is the LWE hard problem? Imagine that we have a matrix in ZQ with coefficients in ZQ. So just a matrix with coefficients between 0 and Q. And we have a public matrix A, and these coefficients are uniformly distributed. And this is public. What we do is generate a small s and e, and with small I mean the coefficients are small, from some small distribution. If we now give an adversary A, the public A, and B, which is calculated as this, then it seems to be hard to recover S and E from this. It also seems to be hard to even distinguish this from just a random sample, a sample with random coefficients. Okay. So how do we make an LWE-based encryption scheme with this? Well, the first thing Alice does is just generate one of these LWE samples. So this is just an LWE sample, and she sends this over to Bob. And now the secret and this E are secure because of this LWE assumption. And Bob does actually just the same thing at the other side, but the only difference here is that he uses A transpose. But exactly the same thing. And second thing he does is he makes a second LWE sample, but now with beta as this uniformly random matrix. And he adds here the message. Now he sends these two samples over. And what Alice is going to do is more or less the same as Bob. So you see here that Bob multiplicates B with S. So Alice is going to multiply B prime with S. And then subtracts V from V prime. And if we calculate this M prime term, we get this. You can do these calculations, I'm not going to go into detail. But this is, well, you see that the message is in here, and there is a lot of noise terms. Luckily, the two biggest noise terms, the ones involving this uniformly random A, they cancel each other out. So we end up with a term which contains the message, and then some, well, small h, depending on the parameters, of course, but we hope some small noise terms. And we do get a failure if we calculate this noise term, and if any of the coefficients in absolute value is bigger than q divided by 4, we will have a decryption failure. And typically the parameters are chosen so that this decryption failure is 2 to the minus 128, but in terms of real security, we didn't really know what this meant, so it was just a, well, educated guessing. So what we're going to do now is, just for the sake of convenience, we're going to rewrite this equation. So we put everything in the secret that Alice is generating, so in this S term, so this and this. In the ciphertext we're going to put everything with a 1 prime and then prime. Nothing much to see here. The only thing is, so we get actually just the same equation as here, but with less terms. It's easier to work with. Also for the sake of the presentation, because I have only 10 minutes, we will do some assumptions. So the first assumption is that we're working with vectors instead of matrices. So in the paper it is generalized, of course, but just for the sake of the presentation. Second thing is that we're going to assume that these are 2D, because then we can actually plot them and make nice graphs. And the third assumption is that this G is actually small, that it's negligible. Also in the paper it is worked out with G, but you can see that S times C, well, it's a multiplication of all these terms. You can reason that it's going to be bigger than this G, which is only one error. But again, if you want to know the details, please read the paper. So, we have S times C in absolute value is bigger than Q divided by 4. Imagine that this is your S. So it's just some vector in the space. We only know its distribution. We don't know in which direction it is. But we know that if S times C is bigger than Q divided by 4, we have a failure. Which is this space. So if the ciphertext is in this space, we will have a failure. Also on the other side, because we have this absolute value. Okay? And so this happens with the probability delta. And we want to improve on this probability. We want to make this, well, have a higher failure probability. So what we can do is, you might say like, okay, let's select a ciphertext that is here, very far away, so that we get a high probability of failure. The only problem is that the schemes are secured with the Fushisaki-Okamoto transformation. This is some hard Japanese names, but what it actually means is that what you're going to do is you generate the ciphertext from a seed. And so you generate them through a hash, through a pseudo-random generator from this seed. And if you input a ciphertext, you need to prove that you actually know this seed. So there's two options. Or we're going to break this hash, which, well, is probably too hard to do. Or we just generate a ciphertext and then we choose whether we accept the ciphertext and we're going to work with it, or whether we throw it away and go for the next sample to generate. And so we just generate a bunch of this ciphertext and we accept it. Accept this ciphertext if the failure probability is high enough. Okay. But remember that we don't know anything about this direction of S. So how can we say something about the failure probability of these ciphertexts, not knowing anything about S? Well, if we write this with vectors, we can write this inner product as the norm of S times the norm of C times the angle between the two. Now, this is something with the secret, has nothing to do with the ciphertext, so we don't know anything about it. This, we actually know. We can calculate it for a given ciphertext. And also this cosine, we don't know anything about it because we don't know the angle of S, so we don't know anything about the angle between S and C. So what we end up with here is that the higher this norm of C, the higher the failure probability. And this is what we're going to use. So this is a circle of norm. We pick a given circle with a given radius, and we will only accept ciphertexts, weak ciphertexts, that are outside of this circle, that have a high norm. Okay? And this will happen with a probability alpha, based on how big the circle is, of course. Then plotting the previous on top of this, you will see that given a ciphertext that is outside of the circle, we actually have a higher failure probability, beta. Okay? So, to find a weak ciphertext, we need alpha minus 1 work, on average. The failure probability, if we have a weak ciphertext, is beta. So how much work do we have to do to find one decryption failure? Well, we need beta minus 1 decryption queries on average, and we need to repeat this whole process. Well, for every time, for every of these beta steps, we need to do alpha minus 1 work. So in total, we need to do alpha minus 1 times beta minus 1 work to get this, to get one decryption failure. Does this improve upon the initial delta? No, because, well, if you count the ciphertext that you generate, which is what we take as a measure, well, you can better input any ciphertext that you take to the decryption oracle instead of withdrawing some. So why would you all do all this calculation? Well, there's three things. The first thing is if you have a limited number of decryption queries. If you can only do so many attempts at getting a decryption failure. For example, in the NIST post-quantum process, they say, well, the maximum number of queries that you can do to the oracle is 2 to the 64. So in this case, you can do actually this pre-computation alpha to lower the decryption, to increase the failure rate of these samples. And then hopefully you get your failures within this 2 to the 64 bounds. So that's the first thing you can do. The second thing you can do is a multi-target attack. You can do this alpha in a huge pre-computation. You put a lot of effort in this, and then you have all these weak ciphertexts, and you can input them into multiple schemes. Now there is an easy fix, and most schemes, such as Saber, Kyber, have implemented this fix, in which the public key is hashed into the ciphertext, into this ciphertext generation, so that there's actually a separation of all these domains. But some of the schemes didn't do this yet, and it's actually an easy fix. They should really do this. The third thing is, of course, quantum computers. We're doing post-quantum cryptography, and we cannot speed up these oracle queries because we only have classical access to a server. What we can do is speed up this alpha, because this is offline work. So we speed up this alpha using Grover, because we're dealing with hashes, so we don't know how to speed it up further. But we can square root this work, and then we have this. And this actually improves upon the previous delta that we were doing. So we have, in all of these cases, computed the efficiency of finding one decryption queries. We generated plots for that. So this is for the quantum attack. And what you see is, on the y-axis, the total amount of work that you need to do. The total amount of ciphertext that you need to generate, of hashes that you need to calculate. And this is the pre-computation that you do to obtain one of these weak samples. What you see is, if you don't do any pre-computation work, then you will end up with this delta that we had before. You just submit you do, like, you generate one ciphertext, you submit it. And you see that if you do some pre-computation, that you can actually get this work down. So by Groverizing this first stage, you can get this failure probability down. This is for various of the NIST schemes. But you also see that it's not a super drastic attack. So you are limited in what you can do. And remember that the provable thing was that this was squared, so it's somewhere here, because it doesn't start from 1. So you can really speed up this whole process, but we're not at the provable bound yet. So or the proofs can be improved, or this attack can be improved. So we've been talking about obtaining these decryption queries, but what can we actually do with this? Because that's also one of the questions. Well, we know that this inner product between S and C is large, or larger than Q divided by 4, or smaller than minus Q divided by 4. But let's say that it's large. This means that there is a correlation between the ciphertext and the secret. So meaning that if we find enough failing ciphertext, we can use any statistical technique, for example maximum likelihood estimation, to estimate this the secret S, or small s and small n. And once we have these estimates, we can construct a new LWE problem that's easier to solve. How do we do that? We have our original B from our LWE problem, and we subtract this new LWE problem we construct with the estimates. And what we end up is that we have a new LWE problem with, well, if our estimate is good, smaller noise or smaller probability distribution there. So, what is now the implication on the schemes with our attack? So you see various submissions to the NIST post-quantum standardization process. You see their original security, and you see the security under our attack. And you see that there's actually, the security goes down quite a lot using our attack with these decryption, using this decryption. And this is quite a big of a reduction factor. We also don't need a lot of decryption failures. The only problem for an attacker is this. The number of decryption queries that you need to do this attack is completely impractical. I mean, you need to assemble 2 to the 131 decryption queries. That's on average what you need to do this attack. So, what's the conclusion of this? Is that yes, you should really take care of this failure probability. It can be really dangerous, and you should not have a failure probability that is too low. But on the other hand, for the schemes that are now in this quantum process, post-quantum process, they are conservative enough in that you need really a lot of decryption queries, an impractical number of decryption queries to get an attack on it. So that's my part of this presentation. The next part is going to be done by my colleague. If there is any questions about it, please.